argue with scientists, there's definitely an impact from carbon and greenhouse gas emissions associated with aviation. Whether what we're talking about by 2030, it could be as much as 20% of greenhouse gas emissions according to IATA, and then non-CO2 effects on top of that. But when a drop of aircraft fuel goes into an aircraft engine, none of that is taxed. That can't go on forever, but of course, who's going to be the first country to start taxing their airlines, and then in a liquid form? And we're talking about why liquid, because it effectively can take 100 seat plus aircraft today off the ground. And they said they need to start last year, 2023, to get their infrastructure in place for 35. So it's 12 years is the lead time.
Ladies and gentlemen, please welcome Paul Perera, a man fighting to make aviation sustainable in an era where airlines treat legroom like a VIP nightclub. At High Flux, he's pioneering cryogenic propulsion, a term so jargon-heavy it's basically Avengers Endgame for engineers. He's the human equivalent of a Swiss Army knife, if that knife also had a PhD in aerospace engineering, a side hustle saving the planet, and a LinkedIn profile that puts us all to shame. Paul Perera has worked with just about every major player in aviation: Rolls-Royce, Airbus, GKN, Biosystems, before co-founding HighFlux. Paul, welcome, and I'm exhausted just by reading your bio. What's the secret, and can you replicate Paul Perera?
I think anyone could have a career profile that has a lot of aspects to it. I think the challenge you have to face up to is that life isn't just one straight line, and take every opportunity as it comes. But as far as where the mission in my life comes from, I guess, and passion is that I've created a fair bit of carbon in my life. I hate to say it, having been involved in aircraft manufacturing with Airbus and GKN Aerospace, and with Rolls-Royce producing dirty, great big kerosene guzzling military aircraft engines. So I suppose where I am now is that I want to right my wrongs and have a mission to do so before I hand over to my next generation. And my next generation isn't driving a car. My next generation travel very little on a plane, and I respect for that, and I feel like I need to make sure that we put back something of a legacy as we head to those years where the planet is going to either live or die on the back of what we decide to do in the next 5 years. That's why
Wow.
HighFlux was created.
What an answer. Why aviation?
Good question. And I think it's a very poignant moment to ask that question regarding hydrogen, all of these other aspects of the energy transition. Let's be clear, there isn't one size that fits all, but the biggest problem that I can personally do something about to solve is in aviation. There are bigger problems in the world, and I'd love to be able to solve them all, but I'm just going to focus on things that I can have an impact on. Why aviation in terms of giving you some numbers? Let's not argue with scientists. There's definitely an impact from carbon and greenhouse gas emissions associated with aviation. Whether you believe that's 2%, which is where airlines would like to say they are today, in the global scheme of things, I think that's very, very underestimating the impact. And if you're a climate scientist, you might put it at 10% today. But whichever way it's going to grow, as more and more of our industry and our daily transport vehicles will turn to electric, then the rising tide will mean that aviation becomes one of those that sticks out, even with every effort that's been put in, not least because we all want to travel, and we want our future generations to be able to travel and connect and communicate and have relationships and build partnerships and build businesses. So aviation has a real purpose in our lives.
Yeah.
And I think that's why aviation beyond anything else.
Why hydrogen in aviation?
So great questions. Keep coming. So let's just understand the situation. Aviation, when we divide it up in terms of carbon emissions, most carbon emissions come from single aisle aircraft. These are our 150 to 200 seat passenger aircraft, probably traveling no more than 2,000 kilometers, thereabouts. And 66% of all CO2 emissions comes from those type of aircraft traveling that range. And with that, you kind of think, well, if that's the biggest chunk that we can look at and as a problem, what's the best solution for that kind of size of aircraft? The battery, even if it trebled, quadrupled, 10 times the power
Yeah.
density of today's battery, is always going to lug a dead weight around with it. Once the battery's spent, you still have the weight of the battery materials. And I work heavily with battery manufacturers as part of what I'm trying to do. And actually, if you think about it, a fuel cell plus hydrogen is a battery. It just happens to be a different form of a battery where the fuel ultimately is the combination of taking the fuel out of green hydrogen, and hopefully it is green hydrogen, and moving that into the aircraft in a liquid form. And we'll talk about why liquid, because it effectively can take a 100-seat plus aircraft today off the ground, but in next to 5 years' time, and I think Airbus agrees with this, they'll be able to take a 150-seat passenger aircraft, and that becomes economically comparable in some respects to our today's, poorest performing aircraft. Now, we need the economics to work out, and hydrogen over the next 5 years will become economically closer to kerosene in terms of cost. And that's assuming we don't tax kerosene. And kerosene today, as many may know or may not know, is not taxed as it's given to airlines from the suppliers, which seems strange, right? Because we all drive
Yeah.
our vehicles around, and every fuel drop we put in our car, at least in the UK where I'm based, maybe 50% of that goes back to government. But when a drop of aircraft fuel goes into an aircraft engine, none of that is taxed. That can't go on forever. But of course, who's going to be the first country to start taxing their airlines? And then, what's the impact of that? You have disproportionate advantage if you don't tax your airline. And then we get into kind of even today's topic of trade wars, and you get into taxation wars. So I think the reality is we are going to tax carbon through different mechanisms. We'll find ways to use the carrot and the stick, and we'll find that even hydrogen comes with a cost of carbon. I'm not going to disagree with some of the people who understand today green hydrogen isn't in abundance, but could it be, and how could we get there faster? I can tell you a lot about that as well. But what I would say is it is that middle of the market sized aircraft, 100 seats to 150 seats may be interesting, but more up from 150 seats to 200 seats that airlines really want when we talk to them.
I would naturally now ask you how far along are we from there, but let's start with what are hydrogen's thermodynamic characteristics compared to jet fuel?
Oh gosh, that's a great question. Then go straight into the thermodynamics, which of course to me is everything. So yeah, thermodynamics. So let's remember that when we look at jet fuel, we typically operate at ambient conditions, and that means that the fuel in the wing, which it is today, occupies the largest amount of space that is available to us, which is the wing void. And having worked for Airbus and wings, we're always looking to see how we can leverage that wing geometry so that we get the best performance out of it. But actually, it's a flying tank. It's a wing that
Yeah.
has it's a fuel tank that has a wing geometry. Um, the key thing about the question on thermodynamics is when you put hydrogen into aircraft, today those that are flying them, apart from a couple, H2 Fly as being one that has flown with liquid hydrogen, most of them are gaseous. So these are high pressure, 700 bar, 600 bar pressures, and they can carry with a power density and propulsion density, close to a battery today. That's not going to be good enough for long range or even medium range aircraft. 2,000 miles. We're going to need to do something to get more energy into a smaller space. And the way to do that is to go to a cryogenic. So this is where the thermodynamics comes in. Cryogenic hydrogen. Cryogenic hydrogen actually is at minus 253 degrees at ambient conditions with probably about 4 or 5 bar in the tank. And what that means is you can actually lighten the tank's mass compared with the amount of energy that you're carrying within it. So we're looking about minus 253 degrees or 20 Kelvin. And that's an important number because it reminds us that we're operating at what we call high temperature, would you believe, superconducting temperatures. The earliest superconductors were operating much lower temperatures even than that. And today in the fusion world, we use temperatures of minus 253 degrees, thereabouts. And that's where the thermodynamic effects come in, where we can benefit from carrying a compressed amount in terms of volume of energy that's highly dense in the form of liquid hydrogen, and we can convert that to help us propel our aircraft more efficiently using superconductors. And we can talk about how superconductors work if that's of interest.
Here's what blows my mind. It's the lightest element, but needs a huge tank. How do you design an aircraft around that?
So we've got 3 ways we can do it, right? So one, we can start from scratch, and then, as I think, many people have seen the concept aircraft with blended wing bodies, integrating the tank much more into the body of the aircraft so that you can accommodate those tanks without compromising kind of fuselage real estate. That's important because obviously the paying passenger doesn't want to be displaced with large tank. So that's probably the clean sheet opportunity. And there's companies out there like Jet Zero in the US who have set up to do just that. There's another way, which is to think about how we can get conformal tanks and put them into safe areas and safe zones within the wing. Today, most of the designs that are being conceived limit the amount of hydrogen that's carried in the wing because we can't get conformal tanks that allow you to carry the hydrogen really effectively. That's something that people are working on. We've been talking to University of Bristol and a number of others today about their different storage systems. And they require new materials, and they require composites to work alongside liquid hydrogen. We can talk about what the challenges are there, but they are being solved. And interestingly, that could be the most promising route to get us closer to the mark of carrying large amounts of liquid hydrogen. And then finally, you have to put some in the fuselage today, and that's the final option. But putting that in the fuselage does mean displacing some space that would otherwise be used for people. But hey, look, we've got aircraft that are flying around in regional aircraft that have their cargo at the back today. So we can manage this. And we've seen various design configurations that allow us to carry up to 80, maybe 100 people in that configuration. I think the question that will always come is probably not to do with, is that the right thing to do? It's about how it will be perceived by our flying public, right? So we're used to having the very interesting model where we refuel the aircraft with the passengers walking on board, smelling the fumes. When it comes to liquid hydrogen, we probably don't have that opportunity because liquid hydrogen still seems to be a little bit more risky when we're moving it from the bowser into the aircraft. But we would probably need to think about how we would also configure the aircraft, allowing people to both do the quick turnarounds as airlines would need at airports. And I think that's where we move towards that blended wing configuration that allows that little bit more integration with today's current infrastructure.
Yeah, we will come to that. That's definitely interesting. When you're putting fuel cells into aircraft systems, what's the biggest headache?
Okay, so fuel cells, we go back one step and just to remind everyone why we put fuel cells into the aircraft, and particularly with a superconducting motor, because the superconducting motor basically operates off electricity. It just happens to be super efficient at running with zero resistance effectively because it's got superconducting materials inside, giving you this really important power density of the motor. But it also requires a conversion of the hydrogen into electricity. And the biggest challenge right now in the fuel cell isn't the fuel cell itself. We can get to power, we can get to densities, and that means the weight of those fuel cells can come down. The challenge is most likely in the thermal operation of the fuel cell, because what it does is it discharges a huge amount of low-grade heat. Today, if it's a PEM fuel cell operating at about 120 degrees exit, then you've got, for every megawatt of power you get, you probably get a megawatt of heat. And so we're operating at 50% efficiencies. That means that we have to get rid of that 1 megawatt of heat in an efficient way or use it somehow. And that's the biggest challenge, because we need great big radiators to get rid of that heat. That's what happens today. Unless we can get to higher temperature fuel cells, which are happening to be being produced. They're just, we're not there in the level of performance that we would want in terms of maintenance, in terms of longevity of performance. We need to make sure that they can last the life cycle of an aircraft, at least as long as a jet aircraft has within its maintenance intervals. And that's the commercial challenge that exists when we're starting to look at hydrogen fuel cells. So it's really two things. It's the performance relative to the thermals, which we've talked about, and it's about the cost efficiency associated with managing that higher temperature fuel cell, and then what you trade in terms of maintainability cost.
How does hydrogen affect the basics like range, payload, takeoff? What changes?
Well, actually, it's a great surprise to most that as you put more hydrogen on board and we want to go further, you get a better range and payload for performance compared with kerosene. Professor Rob Miller out of Cambridge University is a excellent speaker and has done a lot of the analysis on this, and says actually we could fly a wide body aircraft to the other side of the world if we just had more hydrogen available. But actually you don't need to worry so much. As the tank size grows, you get more efficiency out of the tank. It's a surprising fact. So I think the answer to why hydrogen can scale is probably little known, but the landing weight of the aircraft might be a little bit heavier, but we consume quite a lot of that hydrogen without changing the balance of the configuration of the aircraft too much, which means that we can actually trim the aircraft to be at a better efficiency, both in terms of performance of the motor and propulsion system, but also in terms of the aerodynamics. And so you actually get a win-win from hydrogen that we couldn't otherwise get. So the studies done under Fly Zero, which was a Aerospace Technology Institute, a UK-funded, government and industry-funded program, concluded that the best place to start would be on a mid-sized, larger aircraft with hydrogen burning kerosene, rather than kerosene burning hydrogen. And they felt that they could actually make the range of London to Sydney without a stop. So that's the kind of ghost in the room that might actually become really interesting as we look to the future. It might be that the larger aircraft are the ones that are more suited towards hydrogen, and not the smaller aircraft which we're currently playing with in the skies today.
So cryogenic technology, what breakthroughs do we actually need to make this work?
I think we've actually got most of it in our hands. Somewhere in the world, there's someone working on something that happens to be the what I call out of the labs into the demonstration phase for pretty much all the parts of the jigsaw for the aircraft. And why do I say that? We work, and I work closely with the oil and gas industry, who have been operating with hydrogen for over 100 years, maybe 150 years, in its cryogenic form. And it's been used in petroleum facilities, it's used in chemical facilities. We don't have a problem managing hydrogen in some respects at cryogenic temperatures. The space industry has been dealing with it for 50, 60 years at least. The big orange tank that was strapped on the back of the space shuttle, it's 50% full of hydrogen. So we know that it works and it has a huge power density. We can move it around. I would say moving it around is the challenge. When you move it around, you get a condition of boil off. So for every bit of liquid hydrogen you've created, you lose some every day. And the one key feature that Air Liquide and Air Products and other well-known green and blue hydrogen producers talk about is using liquid hydrogen tankers rather than gaseous tankers, because actually they take less space up on the roads, they can be transported more easily, and they actually can shield them with a helium cryogenic layer on the outside, basically a jacket that sits around the liquid hydrogen, so they can make sure that that boil off doesn't actually affect the end result that we're looking for. So you could end up with centralizing hydrogen production and then using roads to take the hydrogen to airports, which may work in some places. In other places, there may be enough demand to create a local liquefaction plant and drive that very close to the airport as an airport becomes a hub. So I would say moving hydrogen around has its challenges. Many of them can be solved. It's easier to move hydrogen in some respects in the sky than it is on the roads. But we've got to solve one thing when it goes to the skies, and that is the kind of the weight of the tank. You know, we can move things around in steel tanks today, aluminium tanks, maybe a bit lighter, but actually
Yeah.
what we really need is a composite tank that can be filled with liquid hydrogen, and that's where some work is really going on right now to address, you know, what the failure modes are, how many times you need to inspect those tanks, how you inspect those tanks, so that we can be assured that we have safety of flight and the chance of any risk or hazard leading to death is less than 10 to the minus 9. So that we're looking at a, you know, comparable safety, if not better safety record than anything else that exists today. And we know that that can be achieved. And so it's only a case of making sure that we put all the right measures in place and that the regulators see that so that they can certify the aircraft. And that's some work that also is being done right now. So whilst we talk about the technology, I don't think there's any risks around that happening to be, you know, it's all about money. If the money's laid out, those products will come to the market. If the regulators see the other industries that have operated with cryogenic hydrogen, then the risks should be mitigated to take that aircraft to the skies. So the only other risk is really making this economically viable. And today, you know, sadly, hydrogen hasn't got beyond the point of, you know, small volumes of green hydrogen, and that's still a big gap. Now, what's good news is, compared with this time last year, we're seeing 3 times the amount of investment going into green hydrogen than we expected. And so there is some pessimism around, I know, on the rate in which hydrogen has been hyped. I think it was overhyped, but now I think we're in a good place where the realism, and we've gone beyond that hype curve and we're into the, you know, been beyond a bit of disillusionment. I think those that really know what they want to do with hydrogen, know the market, are still investing, which is great. So I think we've got the factors of regulation, transportation, and the economics all going to converge within the next 10 years. So I think we've got to see some government support to help that along the way. And I mean, no more government support than sustainable aviation fuel is calling for, but actually you have a much more long-term effect on climate change. So it's worth every penny that is put into this pot right now.
So if I say that hydrogen aviation has started as idea from rockets and spaceships, am I being right?
There's a lot to take from there, but of course rockets and spaceships don't tend to do the number of cycles between one life and the next. I mean, SpaceX is changing some of that, right? So they're reusing some of their propulsion systems. Yeah, but don't forget that probably 17,000 cycles, that means 17,000 takeoff and landings between major overhauls, is something that Airbus and Boeing and others are now, you know, managing to hit. So it's quite a different world when we start talking about the volume of traffic that we're talking to in the single-aisle sector. And so when we look at fatigue cycles, when we look at, you know, potential failure modes, they can be a little bit exaggerated when it comes to aviation compared with space. So we can take more risk in space, is what I'm saying, to some degree, than you can in aerospace.
What are your thoughts on hybrid systems? Is there potential?
Definitely a potential. So we're talking about maybe hybrid in 2 different ways. There's hybrid with, you know, hybrid hydrogen electric, which is what I've just been talking to with superconducting motors. There's hydrogen burn combustion that could be combined with electric. we know that the cruise conditions for an aircraft are when most of the efficiencies could be gained by switching to an electric flight mode, a bit like hybrid cars have today. So you can cruise along the motorway and regain some of that energy as you otherwise be braking, whatever. Maybe if we switched down the size of the gas turbine and burnt a little bit of gas turbine to begin with the flight, get to cruise conditions, and then switch off the gas turbine and then power the aircraft on a fuel cell, that could be interesting. So there are different ways to hybridize, but there's always going to be a battery somewhere in the system. We always have batteries, even in our ICE vehicles today or hybrid vehicles today. There's always more battery than you realize. So I think that there's always going to be a need for batteries. The question is how much battery.
So you spoke a little bit about turnaround times. How would hydrogen mess with turnaround times? Can we still keep these tight schedules?
So look, there's a lot of work that I think two groups, I would say, the International Council of Airports and IATA have done alongside industry, and there are challenges, right, for putting together infrastructure in any airport right now to adopt a hydrogen aircraft. Let's not hide from that. It is different, but it's been done, right? So there are other organisations. I work with Bristol Airport here in the UK who have trialled hydrogen in their airport on the apron. Not necessarily anything more than gaseous hydrogen, but they've gone through all the CAA regulation. The turnaround times associated with filling a hydrogen wing or a hydrogen tank or whatever it might end up being, there is a need to make sure that we have enough time to do that. It could be a factor of twice as long if we don't get it right. But if you can manage that from hydrogen from the very beginning by refueling in two different ports, you can halve the time. So there are ways in which you could resolve that challenge. Turnaround times we talked a bit about earlier when it comes to blended wing bodies. Maybe that's a potential opportunity where you could reorientate the aircraft so you can refuel at the same time start loading the aircraft. Now, those are the kinds of questions that I think the Goliath project that Airbus and Clean Aviation have sponsored with a number of academics. I was reading that report last night, and there were some challenges to achieve that. Safety zones, venting, all sorts of solutions that have been thought through before, but nothing which isn't able to be tackled. And we've got some really clever airport infrastructure people working on this around airports today and thinking it through with huge experience in leveraging that across from hydrogen refueling capability in other industries. So I don't have a problem people saying it's going to be difficult because it will cost us some money, but it will be important for us to think about that isn't a solution that is too far removed from what we have today. And so, yes, it can be achieved. Maybe we need some public money to sort out kind of the Kickstarter of this. We need some airports to be the first adopters. And in fact, Airbus has done a great job at highlighting, I think, 60 odd airports around the globe that are now moving in this direction to de-risk the airlines gamble, if you want to call it that, towards moving away from SAF or kerosene.
So things like flight dynamics, weather conditions, maintenance, inspections, emergency protocols, things like that, pilot training. What changes?
All of the above in some shape and form, right? So let's say I'm going backwards. So pilot training, yes, in every single form of risk management, which is what we're doing here. There are different risks associated with liquid hydrogen and a liquid hydrogen aircraft, but nothing that a pilot couldn't be trained for. Inspection, and by the way, once you train them, then you've got risk management protocols that are managed through, just like when we refuel our cars at the with a petrol tank or gas tank. We're told to put our mobile phones away. We're told to, not smoke. All of those good protocols are put in place for a good reason. Remember, we used to be able to smoke on aircraft before, which is kind of strange when you think what's underneath you. There's a a great big kerosene tank, right? So
Yeah.
we know that there's risk management required. And I think that comes to then the next point going back is inspection. The aircraft needs to be inspected today. There's just going to be different means of inspection. I'm working on some of those today with a number of companies. And really interestingly, there are solutions, but there may be different ways in which we use today's solutions than we would have thought. So when it comes to the tanks, do we actually monitor the tanks as they're being refueled? Yes, we do. Do we check their levels? Yes, we do. Do we use the same level sensors? No. Do we use the same inspection technologies? Probably not. But could we use some combination of different things that exist today? Yes. So you might recognize that there's pressure in the tank, that the pressure reduces when you've got a leak. Well, that is a fairly good indication you've got a crack or a break in the performance of the tank, and to do something about it. So there's all sorts of ways you can combine data together, and I think that's one of the keys that we will need to do as we move forward. In terms of regulation, yeah, that's going to change, and we're working with the likes of the CAA, the Civil Aviation Authority, the FAA, the Federal Aviation Authority in America, and the EASA in Europe, who are all working together to kind of collaborate to find a way to get the regulated pathway for hydrogen aviation within the next 5 years. So I think that, the one big one, I think, is to convince the public that it's safe. And, what better way than actually demonstrate some of these aircraft can fly safely. And, we're prepared to put people inside them. And I think it's great that we're seeing aircraft like Avias and previously Universal Hydrogens and H2 Flyers, carrying people on board and flying. And that's all positive. Now, there's still a long way to go. And we need to make sure that we bring the public with us on this, because that's going to be the big question. I think many people stepping onto a hydrogen aircraft, which may look pretty much the same as today's aircraft, the tube and wing, or may look quite different if we go to a blended wing body. But either way, they'll want to know what's in the back of that aircraft. If that's a hydrogen tank, how safe is it?
Yeah. We'll go a bit more granular with that, but before that, I have one question that you actually just mentioned. How long is that, and what are the factors that can speed it up or slow it down?
Well, I think we've touched on it, and the Airbus has made their own call on this, that there isn't infrastructure in place quickly enough for them to get their aircraft set, and they can take advantage of the time that the infrastructure needs to come along to go another iteration around their design cycle, which means that others could play a role in this. You could see Embraer, who've announced their own Energia hydrogen-powered series of aircraft, maybe smaller scale, 100 seats, maybe minimum size and growing, but would be in their nice sweet spot of regional aircraft, and it could run into the 2030s, early 2030s, potentially, to start putting some flight demonstrators together, late 2030s, to actually have a EIS, entry into service date. Infrastructure then has to catch up, right? So we've been saying that that's one of the challenges. We need investment in that whilst the aircraft is still being developed and designed. So I think that's one of the compelling issues that we have to deal with. One of the ways in which people have thought about this is, well, just bowser the liquid hydrogen to the aircraft and deal with it in a way that we do today. In terms of then the only other thing is the regulatory piece. I think we're only 5 years away from having a good regulatory understanding, so they can set down the codes, set down the protocols, show what they're looking for means and compliance, and hazard analysis, and all the things that we need to put in place. But one thing that I've been working on with a startup company, it's quite interesting to partner with them. They've been leveraging their application of AI in engineering and training artificial intelligence to help get to a quicker route to certification by blending all of the protocols from the ATA chapters, the hazard analysis, together with the means of compliance, which comes from the regulator, and finding ways to get through that process and set the projects that need testing data, validation, and compelling evidence in the journey earlier with the regulators, so that actually, whilst we have this process, we can consolidate that into a lot sort of timescale. So I guess my answer to this is, how can we use today's technology in a way that we couldn't do even last year to compress the timeline so we can make a bit more pace behind us and catch up with what we really need to do is to fly these aircraft in 2035 to make a compelling difference to 2050's carbon and non-carbon effects in the sky. So I think the answer needs to be the other way around. What do we need to do to lubricate this system to move faster? Money, resources, and some real passion, which I think we could find in this world today.
Yeah. Looking at you, definitely. So what prevents, and now we're going a little bit deeper, what prevents catastrophic fuel loss from boil off during ground delays or long hauls? And how do you mitigate the explosive risks of hydrogen in crash scenarios?
Oh, look, hydrogen, that definitely has a number of interesting features to it. So the boil-off process happens to be one of those. Liquid turns to gas. It happens at about 1% of an aircraft tank per day once it's inside the aircraft and not being chilled. Yeah, that's probably fine when we're sitting on the ground, but it does mean that you are losing a range every day that you don't fly the aircraft. Oh, the good news is airlines want to fly their aircraft once they've got the hydrogen on board, and so firstly, let's get the hydrogen on board and let's fly and get the turnaround times to where they need to be. In terms of when you're full of fuel, like we do have the situation with kerosene, sometimes you have to let that fuel go because you've got to do a turnaround and get back to the ground and you're too heavy. The same will happen. Actually, the good news is we don't spread lots of kerosene into a cloud and then fall on the fields around the airport. When it comes to hydrogen, we vent it and it goes vertically upwards. There's a real opportunity. Okay, yes, we lose some greenhouse gases as that hydrogen escapes, but you don't do that every day, and that's really a contingency. So hopefully, actually, is a safer architecture with hydrogen when we have to vent it than it is when you have to lose lots of kerosene. Now, let's talk about a crash situation. Well, everything's designed around crash situations in aircraft. You compel yourself to look at the worst case, and that's your limiting factor for everything. So yeah, every design of every tank will be there for 10 to the minus 9 failure rate. And so whatever the answer, it's 10 to the minus 9 failure rate. So you design for that crash. You design to contain the boil-off gases or vent them beforehand and release them, whatever it might be. But if you haven't designed it with that, you won't get through the certification process. So I don't think it's as difficult as people might want to believe.
Yeah. But when you just say 700 bar, it sounds so,
Yeah, so I'm not saying 700 bar. Actually, when it comes to liquid hydrogen, I'm saying 5, maybe 10 bar, which is not much more than you have in your bicycle, in your tire. So yeah, I don't think it's anything like the 700 bar that we currently have to see in heavy goods vehicles, because that's what they're going with. Yeah, we're talking about liquid hydrogen. At liquid hydrogen temperatures comes under the curve in terms of thermals and the pressures, and we definitely don't see anything like that. So I don't think we see high pressure systems being the ones that would maintain us in the air.
Yeah. I have to say these answers are very informative and come from experience, which is very critical for the people who will watch this. So when superconducting motors lose cryogenic cooling mid-flight, what's the failure timeline and emergency protocol before thrust becomes compromised?
So first thing is you have multiple motors like we do today, but in fact, you probably know this for aircraft running with 2 engines today under ETOPS conditions. Effectively, you have to be able to run that aircraft back to a airport with 1 engine operational. The same is true when we got electrical engine. Now we're talking about superconducting. The good news is you've always got that cooling power with you. The one thing that we worry about most is the burnout of the coils inside the motor, and so keeping those coils at the temperature is key. And so we've got things like trip switches or fuses, if you want to call them that we have to manage to make sure that if the temperature did increase and you weren't doing the superconducting, you switch off and you let that motor go, which means that you have other options on other systems, so you run another system up. What does that mean? You have multiple motors. You're not going to run with just 2 motors. It's most likely going to be 4, maybe even 6. And so that's the first answer to your question. And we condition the motors such that they're not touching the liquid hydrogen, because that would be dangerous. We're keeping that at a distance. We're using helium. So helium doesn't, at minus 20 degrees, it's still a gas. And you pass the gas around the superconducting material, and helium being inert means that there's no sparks that can cause any problems. So we don't seem to have a concern that we can't manage this. We've got proof that it can be managed. We have systems in place that allow us to manage it in the same way that a gas turbine today has all systems to make sure that we don't have a burst disk that goes through the cell and flies into the fuselage. We have to contain it. We contain all the problems associated with a motor that doesn't have liquid hydrogen making its way to the motor. Because we don't use liquid hydrogen, we use the helium instead, and we have a cooling loop for that. And if that fails, we have a secondary cooling loop. So we always have our options and redundancies in aviation, and that's probably something that most people who work in the industry understand. Those that work outside of it think, why do we have so many fail-safes? The reason is we've got to maintain this 10 to the minus 9 risk of failure. So I think everyone should build confidence around the fact that that's what we design to, that's what we plan for, that's where we put all of our hard efforts to provide means of compliance, the methods by which we're going to achieve the product safety, and then we work to it and we design to that point, and we have all of the fail-safes and fail-safes on fail-safes that will be in place.
So laboratory boasts 99% motor efficiency, but real-world conditions introduce vibration, thermal stress, and power fluctuations. What's the realistic net efficiency when accounting for fuel cell losses?
Okay, so that we think it's at about 45% today, and will grow to about 60% when we put it all together. The motor is about 99%, and the efficiencies of that probably won't change. But that's not the least of our problems. The biggest challenge is the hydrogen fuel cell. And why do we have confidence that that's going to change? Well, partly because we see a lot of work going on the materials that will be improving the efficiency, running at higher temperatures, the fact that we can see reduction of platinum replaced by things like graphene. There are kind of ways in which we can manage the efficiencies and the longevity of the product in service, all of which are got steps on the way towards TRL, or flight readiness, I call it, technology readiness for flight, TRL 6. Materials properties in some of the key parts of the system are currently being worked on. I was in University of Bristol just a moment ago before this call, and they're working on the different sorts of superconducting materials, putting them under strain. They actually are working on them for fusion reactors, where their tension that they put onto the what's called REFCO, the rare earth barium oxide conductors with the copper in. Basically, they're stretching them and pulling them after they've run current through them to see if they'll break. And what's good out of all of that is they've proven that they're very robust and that they don't break, even when they have huge current losses, and potentially could be, fatal if it was in an aircraft. But here we're proving it on the ground and in a robust conditions, and testing that material right up to the limit, and it seems to be in a good shape. I mean, I've seen pictures of superconducting materials being hammered whilst they're operating, and there are no sparks flying. They still keep working, which is quite incredible, really. You think about putting a nail into a gas turbine, that would be quite scary, wouldn't it? It does have some real implications when you see those pictures of aircraft that have ingested something called FOD, or foreign object damage. But at least our motors will be pretty safe.
Let's talk about costs. who is footing the bill for the global liquid hydrogen infrastructure, that's required at the airports? And
yeah, today is great. I mean, liquid hydrogen is a huge business opportunity. There's more demand for it than there is supply. So the costs are right through the roof, right? Companies like Plug Power are producing liquid hydrogen, and they're shipping that in North America across the Amazon warehouses, where they're turning it into gas to fuel their forklift trucks.
yeah,
Now, you think about how much we're paying Amazon every day for buying our goods and services, or whatever we might buy, mainly goods. And we're actually paying for that liquid hydrogen within those costs today. It's incredible when you think about it. So it's all about volumes. It's all about scalability. Obviously, when we go small volumes, the costs are high. When you go to big volumes, like 10 tons a day at an airport, rather than 500 kilograms, which is currently where people are in aerospace playing with hydrogen, the costs change, and there's that kind of point at which almost you want to push the costs out of the equation until we get to that mature volume of production. And that's where you require, some intervention from government, or otherwise, big investors that are prepared to bootstrap the industry, which I don't think is necessarily going to come. When there are other ways that they can make their money in AI and other industries that make a bigger return faster. So I think we're ultimately back to, does the government support the transition to not just sustainable aviation fuel as kerosene non-fossil solution, but also liquid hydrogen? And that's the question that I think governments need to be asked across at least Europe, maybe across the world soon. Are they going to invest in time and money into this? Our government in the UK has just been asked by Rolls-Royce, can they have 3 billion build the next generation of single aisle engine? 3 billion would take a motor like ours and an aircraft to the skies, which would be zero emissions, true zero emissions. And they're trying to build something which will be a gas guzzling, kerosene burning, maybe SAF if they're lucky, solution for 30, 40 years. So it's about, what does our government want to invest in? Does it want to invest in one thing, both things? How much do they want to put to each of those options? If I were them, I would be keeping in mind to be balanced, right? So I don't think one's better than the other overall, but let's not rule one option out when it could actually be the real solution to mitigate climate change, both the carbon and non-carbon effects. That's key. I think that's what we need to ask ourselves and our families, as to, where does our taxpayers' money go to?
So in my view, there's a need for hydrogen production that is near the airports, especially big hubs. And the transportation cannot be done by trucks. It has to be by pipelines. And then the storage you mentioned a little bit, but when will green hydrogen production realistically scale to meet aviation's massive energy demands without cannibalizing other clean energy priorities?
Let's think about that last question is the key to the answer, right? So, which is the worst of all evils, right? So, we can produce green hydrogen, but we might want to use it for steel making. We might want to use it for aviation. We might want to use it for shipping. We might, in some countries, we're talking about using it for home heating. Look, I think you have to use the limited amount of green hydrogen for the things that have the biggest carbon effect today. But let's not forget the non-CO2 effects. So I've mentioned earlier, aviation represents itself at 2 or 3% of global greenhouse gas emissions. When we add the non-CO2 effects in, and we actually look at the reality of what we're talking about by 2030, it could be as much as 20-odd% of greenhouse gas emissions, according to IATA, and then non-CO2 effects on top of that, maybe 26%. That makes aviation a target for decarbonisation. And then we say, okay, can we build a green hydrogen supply chain for aviation alone probably not today, but could we think about doing what you said, produce green hydrogen close to airports? Not everywhere. Unfortunately, not
Yeah.
everywhere has sun for solar or wind for wind turbines. And actually, wind turbines by airports are difficult to manage. Um, so you're always at some distance. Then you've got to think about pipelines that don't really carry liquid hydrogen around. That's very difficult to manage.
Yeah.
You only want short runs of liquid hydrogen because of what we talked about boil off. So you're talking about moving gaseous hydrogen around. The real question is each aircraft base, and I mean base because it might not be that they necessarily will all be refueled in the place that they're operating. Um, you might have one refueling stop in the distance, so you might go Bristol to Toulouse, and you might be lucky that both locations have refueling of hydrogen because their proximity to green hydrogen production is good. But they might then fly off to Iceland, and actually there's limited green hydrogen. In fact, probably the bad example because they've got lots of geothermal and it would be a great place to make green hydrogen. But where energy isn't so available in green forms, then you're going to have to make the leg back to find another substitute location for that green hydrogen. So I don't think it's an easy answer, but it's going to be where green hydrogen can be coupled nicely with the kind of wind, solar that sits in that arena around an airport where the hubs will be. That won't be everywhere. I mean, let's take, I know the pictures that people have put around London Heathrow, one of the biggest operations. I really doubt that liquid hydrogen production will happen at Heathrow. But don't forget, there's a petroleum connection line that runs from near Southampton all the way to Heathrow under the ground in pipelines. And that circuit actually was created in about 3 years in the World War, up to World War II. And that allowed actually a link to be made all the way up to Scotland to feed kerosene from Scotland down to the south of England and around the loop of all of the airports. So it isn't beyond the width of industry operations and regulators to be able to put pipelines with gaseous hydrogen and then put liquefaction plants next to the hydrogen that needs to be liquefied at the airport. Perhaps that's the way to work. So can we get solutions that bring hydrogen close to a pipeline, move that in gaseous form along the pipeline, and at the airport you liquefy? That would
Yeah.
be a clever way to do it.
So, but yeah, and there's also SMR, potential of producing near airport. Yeah.
If anyone could produce nuclear power for a reason near a city, it would be for hydrogen production, I think, or data centers. I'm sure we'll be stealing some of that power. But yeah, we've got to think about where the best use of that nuclear fuel, even though it's meant to be cheaper with SMR, it won't be much cheaper, and it certainly won't be as cheap as green and renewable energy. So I think we will have the potential for SMRs. We will need them, but we also need to build out green and renewable energy supplies, electrolysis off the back of that, and as you say, nuclear pink hydrogen, as they call it, to make sure that we've got the consistency that we need for aviation. Aviation flies every day. Hundreds of thousands of people in the sky today. There will be tomorrow, and there will always be demand. So I think the difficult bit is getting to the volumes and scale and finding the clean and renewable electricity at cost. Those are things that can only be resolved by bigger systems thinking than just in aviation.
So, SAF versus hydrogen. Given that SAF works with existing engines and infrastructure, why should the industry prioritize, technologically potentially risky hydrogen as a solution over the simpler carbon neutral fuels that already work? Yeah.
I love this question because it really is. Why should the industry? Industry shouldn't do anything if they want to stay carbon emitting. go and burn SAF, because guess what? SAF still creates carbon in the skies. Yeah. So you still have to then capture the carbon, which the carbon is now being spat out at 36,000 feet. So how's industry really resolving that? Oh, we're going to put lots of carbon capture in place. Lots of carbon capture doesn't exist today. That's going to cost more money than producing hydrogen, and it's going to cost more energy than producing hydrogen. And guess what? Oh, we're going to use hydrogen to produce SAF. Well, that's going to be more expensive than hydrogen by itself. So let's think about it differently. Think about it as a system, and think about who in the actors in the system want to change. Airlines don't want to pay more for sustainable aviation fuel. Someone has to, so it's going to be us as the flying public that pays for that.
Yeah, the passengers.
Right. So now the passengers need to decide: do they want to spend their money on putting more holes in the ozone layer and burning more carbon, or do they want to find a solution that doesn't do that? But that's the choice that we're actually talking about. So when we talk about sustainable aviation fuels versus hydrogen, I don't know what's sustainable about sustainable aviation fuel.
Interesting answer. How do you reconcile the massive energy?
Finished.
Oh,
that was just going to just pose that question. I mean, let's also talk about it. So what airlines, if they're the industry and OEMs in the industry, so making aircraft, Airbus, Boeing, and Embraer, could do is say, oh, let's push the problem to the supply chain of fuels. And that's easy. That means that you don't have to change the infrastructure. You don't have to change anything.
yeah.
But of course, someone has to pay for making sustainable aviation fuel. The infrastructure, the final investment decisions on all these SAF plants isn't happening. Investors don't want to put their money into it yet. So what does that tell you? There's not a good business case. They won't get their returns. They want 20-year returns for 20 billion investment. They can put that money into other things. Actually, when you deconstruct the business case for green hydrogen electrolysis, there are many more use cases for green hydrogen than just sustainable aviation fuel. And by the way, they haven't even committed to how they're going to get the carbon out of the skies. And when you start adding that to the calculation, the investment requirements for that to go alongside production of sustainable aviation fuels will push the volume and demand, I think, down the line. I think sustainable aviation fuel economically won't make sense to anyone. So I don't think we have to argue whether one's better than the other. Economics will do that for it.
Yeah. Talking about economics and efficiency, how do you reconcile the massive energy waste in hydrogen liquefaction? 20% loss even with future tech, with claims of a cost parity.
Future tech is saying 4%. I'm working with a company in Baker Hughes that's doing that work right now. So, liquefaction of hydrogen is a cost, but it's not anything like the cost of carbon capture. So I'm really interested to hear the views on, can we move liquefaction capability on? We haven't touched it for 60, 70 years, really, the liquefaction capabilities we're using today. But the teams that are working on that can see a route to a 4% rather than I think it's more like 12% today, burden on the cost of energy to create liquid hydrogen. So, yeah, we have to work on all fronts, but that's on its way. And I'm pretty confident that will happen. Interestingly, there is a role for superconducting motors in liquefaction, but we can come on to that another time.
So I will go off the script a little bit. Talking about carbon capture, what do you actually think about it?
Well, look, I'm working with the companies that are working on carbon capture, direct air carbon capture and point source. Whichever way we look at it, I think they are very difficult to make cases to show the economics works, really, unless we put carbon taxes onto people, and then it makes sense to sequestrate that carbon and put it under the ground and bury it. and we're going to need to do some of that, and we're going to need to do a lot of it at the moment at the rate we're not decarbonising most of the industries that we're working in. So I don't think it's a case of it won't happen, but I think it's really expensive, and the best way to avoid carbon is not to create it in the first place. And so this is what worries me most about sustainable aviation fuels. We're still putting carbon into the skies at 36,000 feet, and it takes hundreds of years to get it back out of the skies. So I think particularly with direct air capture, I think some economics will say that's not going to be very successful at scale. I don't think that's necessarily true. I think we're going to see better absorption methods that we can see with organic frameworks, multi-organic frameworks, MOFs. I think that technology will mean that we can sponge up more carbon out of the air. So I think that there's technology improvements that will move us along. And so we need all of these things. But in isolation and for aviation, it's never going to satisfy the business case. So that's why I believe we have to have something more than just that.
I feel this conversation could go on for a long time, but I will ask you a few more questions. I'm very interested at, and we will potentially continue in our face-to-face series. So if electrolysis efficiency doesn't reach projected 80%, how does the math hold for green hydrogen production at scales needed for aviation?
I don't have the answers on all of this, but I spoke to ITM Power. Their stack production efficiency improvements over the last year have improved by a good 20% plus, maybe even 90% in some areas. So they're all getting better and more efficient. So give it another 5 more years. Let's hope that they are at a better ratio. The second thing is, I think you look at it and say, is there any other way we can produce hydrogen or get hydrogen? Fantastically, I don't know if this is an April Fool's thing, but the French have found tons of hydrogen buried underneath the ground. So maybe there are other places in the world that there's hydrogen just lurking to be found. And we've got lots of ways we can get to oil, and we've got lots of ways to get to gas. So why would it be difficult to get to the hydrogen?
Yeah, there are reasons. I have a full playlist of interviews on the natural hydrogen topic, and they are amazing. But that is very important topic in a future of hydrogen. If that one works out, the world could look very different from today. So how do you overcome the chicken and egg problem where hydrogen aircraft won't scale without infrastructure, but infrastructure won't be built without aircraft demand?
Really easily, I think you club together with the likes of Airbus, and you club together with the likes of Embraer, and you say hydrogen is happening just as SAF is happening, right? And then you say you have to be ready for it. And here are our aircraft, and this is our path to giving you those aircraft, and companies are buying them. We know airlines will buy them when they're available, so the demand is there. We know that there's a premium potentially that will have to be paid. We need to mitigate some of that cost. And we have to then start putting the infrastructure in place now. And I spoke to Geneva Airport back in the year I had with the World Economic Forum last year, and we talked about how long it would take them to get their hydrogen infrastructure in place based on what they knew. And they said they need to start last year, 2023, to get their infrastructure in place for 25. So for 35. So it's 12 years is the lead time. So if we don't start now, it will be another 12 years. So the chicken and egg, I think you have to break it and say, you have to go now. Airports are doing so. Great airports are already making that investment decision. I'm working with a number of, as I mentioned, Bristol being my favorite because they're close to the airport model of a hydrogen hub. Airbus has recognized that model could work for them and supporting them. We've got GKN in the area. We've got a port producing hydrogen coming along. It's going to be a really interesting model. So I'm right in the heart of this space, physically pushing that along, making it happen, demonstrating it at a scale. And yeah, I have confidence that once we've demonstrated this works at some smaller scale airports, the bigger ones will pick it up. So that's the journey. In terms of the aircraft, I have no doubt that thousands of people across the globe that are working on hydrogen aircraft, the research pushing that into the skies will happen, and there's an absolute need. So thank you for the opportunity, Johannes, and we look forward to kind of continuing the conversations. But I'm hopeful, I'm positive, and I think we have a great future of green, clean skies with high flux, hopefully powering some of those motors. We look forward to sharing the story with you.
And I would love to hear more about the high flux, definitely. But in our future conversations, for sure, maybe even to give us a webinar on what you're really doing, because it's very worth of the time of our viewers. Thank you so much for this very optimistic views, and hopefully talk to you soon.
Yeah, pleasure. Thank you so much.
Looking to amplify your brand in the hydrogen energy sector? Welcome to H2 Energy News, your go-to platform for impactful industry insights. Every month, we connect with over 80,000 visitors and generate more than 251,000 page views. Our reach is unmatched, with over 1.2 million web impressions and a loyal social media following of 9,000 plus. Our newsletter reaches 77,000 plus subscribers, decision makers, industry leaders, and innovators. Want to target specific markets? Our geo-targeting capabilities cover Europe, the United States, and the MENA region. We reach key stakeholders, 27% senior executives, 32% directors, and 20% owners and partners. H2. Energy News isn't just a news platform, it's where the hydrogen energy community converges to shape the future. Join us and let's make an impact together. Visit energynews.biz and take your brand to the next